All right, so today, lecture 18. It's good to see you all. Today we're going to pick up on GM, which we didn't finish. So let's review where we were last time. For the GMM system, all GMM systems, we established this was the particular diagram to consider, where Q sub n prime is the number that are found by the arrival of the end customer. Here's its definition. Number found by the arrival of the end customer. After that end customer arrives, a little while later, the next customer, n plus 1, arrives. And he finds Qn plus 1 upon his arrival. Now, during this interval, this inter-arrival interval, a certain number of customers get served. We're going to call that quantity Vn plus 1 prime. It's a number served between the arrival of Cn and Cn plus 1. Here's the definition. And we're using primes to separate this from the mg1 notation with q's and v's. Now, it's very easy to see that this is the defining equation relating those variables. Let's see what it says. It says the number found by n plus 1 is the number that n found plus n minus all those that leave between those two inter-arrival times. So it's a pretty simple equation. And those points, these blue points, when you're measuring how many of a customer finds upon his arrival, is a sequence of embedded Markov chain points, which means if you give me basically the number in system at one blue point, that's all I need about the past to do as good a job as anything else in calculating the number found by the next arrival. So we established that. So what's important is to find the transition probabilities between the number found by the next guy given how many found by the previous guy. Those are the transition probabilities. And last time we developed the elements of this capital P, this transition matrix. There were 4 regions and we defined each one. And of course, we're going to put these transition probabilities into a matrix which we define as capital P. P is the transition probability matrix. Now, let's define the limit called Rk of the number found by an arrival. The probability that number is equal to k. And the limit of that is this equilibrium probability, R sub k. If we now take those r's and put them into a vector, which we denote by r with a vector sign below, our job, as we pointed out last time, is to solve for the system of equations r equals rp, which is very much like pi equals pi p. And again, where the transition probability matrix is defined as this. Now, last time, we looked at a particular region for the ij transition matrix, and we used our intuition to try to guess what, in fact, the Rk would be in that region. And we found out that this was a good guess as to what the Rk should be for k equal m minus 1, m, etc. Now, the only way to prove that's correct, if we're guessing it, is to plug it into the defining equations, namely this set of equations, and see if it satisfies them. But there are some unknowns at this point. We don't know the first m minus 1 r's from 0 to m minus 2, and we don't know this constant k to be defined later. But meanwhile, let's continue with this. We were able to show that this quantity sigma, which appears everywhere, is found simply through this functional equation. We know A star, it's a GM1 system, so you're going to give me the A star, the inter-arrival time transform density. We call that A star. And sigma is equal to that transform of the inter-arrival time density at this value mu minus mu sigma. And we're looking for the sigma, the unique sigma, which lies strictly between 0 and 1. That's how you find sigma. We also showed last time what is the probability that an arrival must q. And we found it's simply equal to this in terms of the known sigma and the unknown k. And we also found out for all GMM systems that the queue size equal to n is equal to this very nice geometric distribution for all n. So you find sigma simply through this equation, and you already know what, in fact, the queue size will be once there is a queue size. Furthermore, we showed that the density for waiting time, this is the density, given that the arrival queues, is given exactly by this equation. Again, sigma is the only unknown. We can find that from this equation. M we know, that's GMM. Mu we know because we've told you what the service time density is. It's mu over S plus mu in terms of transform. So basically, we've solved the system GMM with some unknowns yet to be found. We don't know this number K, as we saw above, up here. And we don't know these first m-1 R's, this number here. We're going to set out to do that. But before we do that, I want to consider solving not the GMM, but the GM1 system. So let's consider that. Let's look at GM1 as a special case. Now in that case, if we go back to our expression for RK, remember we assumed that RK behaved in a certain way from m-1 on up. Well, m in this case is equal to 1. So we're starting with R sub 0, R1, etc. So we can easily write down that R sub k is equal to that thing on the right of that vector, namely it's k, capital K, sigma to the k. And this is for k equals 0, 1, etc. So for GM1, we don't have to find these, but we do have to find k. So now I ask you, given this equation at the top of your screen, how would you find capital K? What's the approach? What would you do? Well, it's pretty clear what I keep drumming into your head, that the summation of the probabilities goes to 1, and that's visible in a number of different forms. In this case, we simply say that it goes from 0 to infinity. And what is that sum? Let's write it out. Summation of capital K, sigma to the k, from 0 to infinity, which is equal to k times our good friend 1 over 1 minus sigma. So clearly k is equal to 1 minus sigma, which means finally that R sub k is equal to 1 minus sigma, sigma to the k. And that's for all k, 0, 1, etc. And that's true for all GM1 systems. It's geometric, which is lovely. Now the only unknown there is sigma. And how do you find sigma? From our expression above, up here, from this one, m is equal to 1 in this case. So we know that sigma must simply be equal to a star of mu minus mu sigma. That solves all GM1 systems. They're all geometric in terms of the number found by an arrival. Now, as an aside, RK, remember, is the distribution of number found by an arrival. RK. But we know that RK in general is not equal to PK, the number found at any point in time. As an example, what is R0? R0, coming from the equation above, is simply 1 minus sigma. And what is P0 for any GM1 system? In fact, for any GG1 system, we know it's equal to 1 minus rho. It's the probability of finding the server idle. And clearly, P0 is not equal to R0 as an example. But I can tell you on the side, we're not going to prove this, so let's point out we can show that pk, this is for gm1, is equal to rho times 1 minus sigma, sigma to the k minus 1, which is equal to rho times r sub k minus 1. Again, pk is not equal to rk, but it's close. It's shifted down by 1. Okay. Having done that, now we've talked about the number found by an arrival. Let's talk about how long we wait. So let's look for what I like to call the unconditional waiting time. Now, first of all, and remember, this is for GM1 still. Remember that the probability that a customer must wait in this case is what? We've already solved it. That's 1 minus the probability he doesn't have to wait, namely, it's 1 minus R0, which in fact in this case is simply equal to sigma, since we know that R0 itself is 1 minus sigma. Now to continue this argument, I'm going to let the quantity capital A be the event that an arrival must queue. And now I want to write down the probability distribution function, capital P, capital D, capital F, as follows. And what I'm going to do is give myself a little more space here. So let me just do something you cannot do easily. I'm going to move this over to here. Let me move this over. Give myself a little more space here now. Okay. Now what I want to write down is the following PDF, namely capital W of y, and what is that? That's equal to the distribution of the queuing time. It's a probability that the queuing time is less than or equal to y. That's our old definition from day one. I'm going to write that down using a condition. And first I'm going to write that down as 1 minus the probability that the queuing time is greater than y. So it's 1 minus the probability that the queuing time is greater than y. That's 1 minus the probability is less than or equal to y. But I'm going to put a condition on it. The condition is going to be A, the probability that the arrival must queue. And if we're going to uncondition that, I'll multiply that by the probability of that condition. But I have to take all possible conditions if we're going to do a conditioning. The other condition is the probability that the queuing time is greater than y. Given a complement that the arriving customer does not have to queue, times the probability of a complement. So that's a correct equation, obviously. Now, let's look at this term here. What's the probability that a customer waits more than y seconds in the queue given a complement, given that he doesn't have to queue? Clearly, that probability is 0. There's no probability of waiting more than y, given that you're going to spend 0 time in the queue. And we also know that the probability of this event A, namely the probability that arrival must queue, we talked about before. Probability of arrival queues is given up here. Remember, m is equal to 1 now. You take 1 minus that, basically. So we're going to get that this quantity PA is simply equal to sigma. Now, we already know from this expression here that the density of the waiting time, given that you must queue, is given this. I'm talking about the distribution, so I have to integrate that and take 1 minus and put m equal to 1. When I do that, this term here is given by 1 minus the integral of what I just showed you. So capital W of y, namely this thing right here, is equal to 1 minus that integral of the function upstairs times the sigma for p of a. So it's sigma, and the rest of it is simply, when you integrate, e to the minus mu, 1 minus sigma y. And that's for y greater than or equal to 0. Now what I just wrote down is basically good for all GM1. Everything in this page above. And let's draw this last function, this distribution, for the waiting time. So what I want to do is I want to plot the waiting time distribution given the equation at the bottom of the page above. It's clear that when y equals 0, this expression is 1 minus sigma. In other words, this goes to 1. So we're going to start off at the origin of this axis, where w of y is equal to 1 minus sigma. And then it grows up and limits to the value 1 up here. And the expression is what we had there. It's 1 minus sigma e to the minus mu 1 minus sigma y. All GM1 has that distribution for waiting time. Okay. Now what's the mean of this? What is capital W, namely what we denoted by capital W, the mean waiting time? Well, we've seen the expression for capital W of y before. We've integrated many times to find its average value. And that turns out to be, if you will recall, simply sigma over mu 1 minus sigma. So that's a lot of information about GM1. It tells us, first of all, that R sub k is 1 minus sigma sigma to the k. Finding sigma from this. It tells us that the waiting time distribution for all GM1 is this very nice exponential, which I've drawn below. And here's the mean waiting time in GM1. The only unknown is sigma, and you find it from that simple equation. Okay. Now, GM1 is nice, but we know a particular GM1 system, which we've studied before. It's called MM1. So let's take that specific case. Now, for MM1, we already know some stuff. We know what A star of S is. It's an exponential. So A star of S is simply equal to mu over S plus mu. So our first job, I'm sorry, it's not mu, it's lambda. We use notation lambda for the interarrival time density. Now the first thing we have to do is find this magic number sigma. That's the big issue, so let's solve it. How do we do it? Remember that sigma is equal to A star of mu minus mu sigma. So that's equal to what? That's equal to lambda over, in place of S, we put mu minus mu sigma plus lambda. You work that out, and if you multiply through, you're going to get sigma times its denominator, so we're going to get a mu sigma minus mu sigma squared plus lambda sigma, and bring the lambda in, well, that's going to equal lambda, of course. It's a second order equation. We're going to find it. We obviously, sigma equals 1 is the root of that second order equation. Sigma equals 1 is always a root. How do you know that? Well, look at this expression over here. Sigma equals 1 means you're talking about A star of mu minus mu, A star of 0. A star of 0 is 1. Sigma is 1. So sigma equals 1 always satisfies this equation. It will always be a root of the polynomial that we're generating here. So you get rid of that one, and the remaining root is simply sigma equals lambda over mu. So we know that Rk is equal to 1 minus sigma, which is lambda over mu. What's lambda over mu? It's rho times sigma to the k, which is rho to the k. Sure enough, we've seen that before for MM1. That is the MM1 solution. And so that's the end of what I want to do with GM1. Let's go back now to GMM. We have to find the boundary equations, if you will. It was K, R0, R1, up to R sub M minus 2. So I'm going to write the overall vector that I'm looking for, R, is equal to the infinite number of them. And I'm going to multiply, I'm going to factor out of this thing quantity K sigma to the M minus 1. Because, you know, that's the form of the values of R beyond M minus 2. So let's write that down. Factor that out, and we're going to get a capital R0. Clearly, K sigma M minus 1 times capital R0 is little r0. I'm using that substitution. I'm using the capital letters now for the unknowns. R1 up to R sub M minus 2. These are the unknowns now. Comma. Now, what's the next term? What is sigma? What is R sub M minus 1? It's K sigma to the M minus 1, which I factored out, so it's just 1. The next term, of course, is another sigma. Sigma starts climbing here on out to infinity. So I know the tail of this thing. I'm looking for things up front. And let me point out what I've done where the quantity R sub capital K is equal to that normalized value. It's little r sub k times sigma to the 1 minus m, that was downstairs, over k. And this is only in the range k equals 0, 1, up to m minus 2. Now, that's a funny thing. I want to define something new now related to that constant. Define a quantity j, which is simply equal to k sigma to the m minus 1, the thing I factored out of that bracket, the vector equation. And so how are we going to find these unknown r's? Well, we haven't used some of the equations that we had, the first k minus m minus 1 equations. We used them for the region 3, where the server was always busy. But now let's take those earlier equations and we'll get the following. So basically I have to write down the equations I haven't used are the equations that r sub k, this is the vector equation, equals the sum from I equals k minus 1 up to infinity of r sub I times pik. And the pik's I found from the regions 2, 3, and 2 and 4 and 3. And this is for k equals 0, 1, up to m minus 2. These are the equations, the r equals rp equations I haven't used yet, okay? And what I've done, I've clearly done something funny here. I've defined capital R beyond this region. So I've defined capital R in this region, so let me say that explicitly so you'll remember it, okay? I'm letting R sub I equal sigma to the I minus m plus 1 for the big I's, for I greater than or equal to m minus 1. And the unknowns are the first few of these guys. Those are the ones I'm looking for. Now I'm going to write this equation in this as a form of, instead of one sum, it's a form of two sums. I'm going to write down that r sub k is equal to the same thing I had, which is the sum from I equals k minus 1 up through the range I'm looking for, which is m minus 2, of the ri's times pik, plus the tail, which is the sum from m minus 1 to infinity of what times pik? What is capital R in that case? It's these numbers here. I already know they're forms of sigmas, so let's write that down. That'll be sigma to the I plus 1 minus m times pik. Now let's solve this thing for the lowest Ri that exists. What value of I gives me the lowest index on these unknown R's? Okay, again, these are the ones I don't know. I'm looking for this set now. What are the ones I don't know? Well, what's the lowest number? It's when I equals k minus 1. So let's pull that term out and put it on the left-hand side. Let's take out R sub k minus 1 times its transition probability, pk minus 1 to k. And that's equal to all the rest. So let's put that down. If I take this one term out and throw it over here, all the rest goes on this side, and I've got to divide by something. So let's write that out. On the right-hand side, I'm going to get R sub k itself, which was on the left-hand side. Oops. That's this term here. Minus, and by the way, I'm putting a minus sign in the whole thing, minus the rest of this first sum, which is I equals k now. I took the k minus 1 out, up to m minus 2 of R sub I pik, plus this term on the right, which is the sigma term. Let's add that. And that's again a minus because I put a minus on everything. That's from I equals m minus 1 to infinity of sigma to the I plus m minus 1, I plus 1 minus m. And I'm going to move it all over because I ran out of space. All of that times pik. And downstairs is the rest, is basically I'm going to take this term. I'll do it in just a moment, but I'm going to take this term, and mark it in red, take that factor and put it downstairs. Okay. Now if you look at that, by the way, let's put down the range for k while we're at it. just as before, from 1 up to m minus 1. Okay, now you look at this set of equations. The r's are the unknowns. It's a triangular set. If I start with r sub m minus 1 equals 1, there's only one unknown. So let's start with r sub m minus 1, which we know is equal to 1. Remember, that's this term up here. Here it is. There's the 1. So I know that. And solve recursively. Keep bumping the index up by 1. Over what range? As I go backwards now, I equals, I'm sorry, k. We're working on k now, sorry. Starts with m minus 1, comma, m minus 2, down to 0. And that's how you solve for the r's. It's a recursive process. But in principle, we can get it. Okay? Now, I still have to get k, which means find j. And we know again that the summation of the rk's is equal to 1, just like before, from 0 to infinity. And that's equal to k sigma to the m minus 1 times the summation of the rk's again from 0 to m minus 2 plus k sigma to the m minus 1 times summation of sigma j from 0 to infinity, and we know what that is. That's a 1 over 1 minus sigma. So I get the expression j, and I'm going to pull j out because this little k sigma to m minus 1 is j. So I get j times that summation of r sub k. And I'm going to divide the whole thing by sigma to the m minus 1, obviously. And this ranges from 0 to m minus 2. Plus j times that summation, which is 1 over 1 minus sigma. All of that equals 1. So finally, we get the expression that j itself, in terms of the r's, is 1 over 1 minus sigma plus that funny sum of the now known r's, k equals 0 up to m minus 2, those unknown r's, of r sub k. So in principle, I've got the j's, which is the k, and all the unknown r's through this recursive equation. So the point is, that's the process you use to find those unknown constants. Okay, now we want to go after the distribution of waiting time for GMM. So let's write that down. Remember, this is GMM. So let's start off by finding the probability you do not wait. And that, by definition, in terms of the cumulative distribution, is capital W of 0. That's the probability you don't have to wait. And what is that? That's a summation over all the RKs when you arrive from 0 to m minus 1. That means you find at least one server idle. So you don't have to wait, okay? And what is that? We figured that in terms of our constants. That's a summation of capital J R sub k from 0 to m minus 1. And in principle, we have those numbers now. Now for k greater than or equal to m, you have to wait. An arriving customer must wait until how many customers depart? K minus m plus 1 depart before he goes into service. And that's his waiting time. During that period, if he has to wait, all M servers are busy. So they're popping out at the rate m mu. And how many? We have to wait for k minus m plus 1 of them to pop out. So how long to get that many out at a rate m mu? And what's that distribution called? That's the Poisson distribution. So let's write that down, okay? So for k greater than or equal to m, the probability that the waiting time is less than or equal to y, given that you found k in this region, by the way. So let me say this is again for k greater than or equal to m, is equal to the integral of all possible values of time for that to happen, of getting k out in that time. To get k out in that time is mu x k minus m over k minus m factorial. All of that e to the minus mu x dx. In other words, whatever that time is that I have to wait, I got to get k of them out. And by the way, why is it k minus m upstairs at the exponent and the factorial? Because for the Poisson expression, it's k minus 1 over k minus 1 factorial. If you remember, with the probability of getting so many arrivals in an interval of time, it's that number k minus 1. And I took the minus 1 off this. So this minus 1 here went away. I took that away. Okay. Now I got to remove a condition on k, right? So let's say that. Okay. And I'll get the distribution unconditional, which is what I'm asking for. Probably waiting time less than or equal to y, which we know is our capital W of y. That's the name of our distribution. And that's equal to the following. W0, the probability you don't have to wait, plus all of this that you have to wait, times probability is k, which is the RK that we know in this region. So I'm going to put the J in here. And that J comes from basically the J sigma to the RK, sigma to the K. And I get the sum of all possible values of K when I have to wait, namely K equals M on up. Just a moment. K equals M to infinity. That's how many could be there. And then I'm going to integrate that I had before, the number of arriving in that period, the same factor here, mu x to the k minus m over k minus m factorial. I'm going to move this baby over again. Then I got to put the sigma term in there. I haven't finished putting the RK. So it's sigma to the k minus m plus 1. That's how many had to be there when I came in. All of that e to the minus mu x, that came from the density itself. All of that dx. So let's move the summation. And by the way, let me just make sure you understand what I have here. This, whoops, let me do this in green. This with this is RK, the particular k minus m plus 1. And that's removing the condition. That's what I was doing there. Okay, let's do that summation then. So this is equal to W of 0 plus J sigma. I'm going to pull one of the sigmas out. That plus 1 sigma right here. I'm going to pull that out. So everything else is a K minus M, K minus M, K minus M. Okay. Then I'm left with the integral 0 to y. Remember, I have to be less than equal to y, so I'm integrating only from 0 to y of what I had, which is mu. And now what is that summation going to be? Take the mu out. I got something to k minus m or k minus m factorial, something else to the k minus m, summed over all values, because k minus m starts off at 0. K starts off at m. That's an exponential, right? That's the definition of the exponential series, as we've seen so many times, that I argue you should learn in high school. And I'm told you probably didn't learn that in high school. But you learned it somewhere before you came here. Okay. So we get this. So we're going to get the integral of mu, and a nice exponential now, e to the minus mux times, first of all, I got a 1 to begin with. That's this one here in green. In addition, I'm going to get 1 for the summation, and that's going to be a plus sigma, so inside it's a minus sigma. All of that dx. Now we should plug in for j and w of 0. We know w of 0. We just gave it up here on the top of the page. If you plug that in, you're going to get capital W of y is equal to, as we know, we'll plug in the w of 0 as well, and we'll get the following expression. Upstairs we get sigma e to the minus mu 1 minus sigma y. And downstairs we get 1 minus, all this about the constants, 1 plus or 1 minus sigma times the summation of nasty RKs from 0 to m minus 2. Those are the ones we had to solve for of R sub k. And this is for y greater than or equal to 0. And that is the unconditional waiting time for GM1. All GM1 systems have the unconditional waiting time, which is exponential. And all you have to do is find those RKs and the sigma. And there's an accumulation at the origin, we know, of W of 0. Now, suppose we wanted to find the average weight, W, in GMM, which we denote by capital W. What's the average time you spend in the queue? Okay? So you can do it a couple of ways. One way, work on this and use the moments and the integration, etc. It's a little bit sloppy. Or you can do it by direct argument. Let's do it by direct argument, okay? If a customer finds k greater than or equal to m in system when he arrives, then again he must wait for k minus m plus 1 to leave. Before he gets a free server. Each service, as I said before, is on average 1 over mu seconds. It's exponential, gm. So sum of all cases, the expected value of the random variable waiting time, which we denote by capital W, is equal to the sum of all values of k from m to infinity. How many do you find busy? of 1 over mu is how much each one takes, and how many have to go? K minus m plus 1, times the probability that you found K in the system. But, happily, Rk is equal to K sigma to the K in this region. All servers are busy. And we did that last period. So let's write that out. So W is equal to the sum, K equals m to infinity, of K over mu. Let me take all of that separately. The K came from the Rk, namely the K I put here is the K that's there in front of each of the Rks. And then I got how many of these? K minus m plus 1 like sigma to the K. Now to sum that, I'm going to take out a factor, sigma to the minus m, and put it right back. And so the sum that's of the form n plus 1 sigma to the n. Sum it. You've done that many times before, okay? And you happen to know from this class, if not from before, that's 1 over 1 minus sigma. So this sum with that is 1 over 1 minus sigma squared. So the whole thing is equal to K over mu times the red sigma m I took out times the 1 over 1 minus sigma squared. And I may as well write that in terms of J. It's a little easier. So I find that capital W, the mean waiting time, is equal to the following ratio. It will be J times sigma over mu 1 minus sigma squared. That's a very nice result. We did it directly now. So let's box that. Done. You know J, you know the RKs, you finish. That's the mean waiting time in all GMM systems. Sigma you know how to find. Again, sigma comes from that functional equation involving A star. Okay. Done. Okay, we're going to move on just a moment. Before I move on, you will note that I gave you a new homework assignment. I put it in, I think, on Saturday. It's due Wednesday night. Next class on Wednesday is the last class we have. So do the assignment. They'll get signed, graded in the same way they do, did you do the work or not. And probably tonight or on Wednesday night, I'm going to assign another homework assignment just for you to play, which means I want you to get familiar with the material we just finished covering and that we're going to cover the rest of today and on Wednesday, namely GG1. You have to say that respectfully. We're entering the world of GG1. Imagine, before you came here, do you think you'd ever be able to do GG1? Well, you still won't be able. No, we'll get it. It's going to be a very nice process. It's a very nice derivation. But I want you to do that because I will undoubtedly ask you something on the final exam, which happens a week from today, about GG1. I can't not test you on GG1. It'll be relatively straightforward. And by the way, I don't know what room they assign the final, but is this good? I was going to say no matter what, it's going to be here. So it'll be here at 8 a.m. Yeah, you got to wake up early this time. Will you wake him up? You wake him up so it's sure to come, okay? Everybody's smiling this nervous little smile. Let me tell you, you folks are lucky. I used to teach this class Monday and Wednesday, 8 to 10. And everybody showed up. And why did I teach so early? What terrible time? Because if I taught it in the afternoon, I'd spend all day preparing, I'd get nothing done. So I'd stay up all night getting the class ready, and the rest of the day at school, do some good research. And so you're lucky. 2 to 4, can't, 8 a.m. Monday. Okay. So look, let's take the break now. Come back, please, in 10 minutes at 3:47. I'm sorry, 2:57. 10 minutes. Yeah, please. 10 minutes. Come back. Okay. This is about to go, but we can change this now. And maybe I'll run a little over. Okay. That's for the television audience. Many ways that we're going to take a particular approach. And I will warn you now, we're going to go through a lot of complexity. I mean that in two ways. One, confusing stuff, a lot of terminology, a lot of new notation, and some complex variable theory as well. As I've done to you before, I'm going to take you deep dive. Not the way a mathematician would. They would take you really deep, you never come back. Okay? I'm going to take you deep, and they're going to bring you back. And when you're done, we're going to have a rather straightforward algorithm for solving GG1. And there's only one hard part when you're all done, and guess what it is? You know what it is, I keep telling you. Factoring, finding roots of a polynomial. Once again, that's the only hard part. Okay? That's what computers are good for, cranking out numbers, okay? So don't get discouraged when I take you down, even if you don't follow all the details. I'm going to quote some complex variable theorems. I won't prove them. I'll take advantage of them, and you will enjoy it, I hope. But the beginning, and by the way, this particular approach, just like our other approaches, has the following two phases. The first phase is where you have to think as an engineer, as a scientist, to understand the physics of the problem and decide, well, if this happens, then this happens, and these people go here, and this happens. And then we end up with a set of equations which describe the physics. Then you got to solve those equations. Then you become the mathematician. You have no idea about the physics anymore. It's all about solving equations and wondering about complex variable theory and all the rest. So we'll go through those two phases. And the first part now we're going to start with will be the physics part. Okay, so let's get this going. Great. Okay, so now, as I said, there are many ways to solve this. And the method we're going to use is basically called the method, it's going to be a spectral method. Spectral as in frequency. And in particular, the one we're going to use is called Lindley's integral equation. We're going to find something called Lindley's integral equation. And we're going to get to that with the physics, then we got to solve it. That's when we go to the mathematics. And I will warn you right now, this equation is of the Wiener-Hopf type. Now, I doubt that any of you have ever heard of the Wiener-Hopf equation, but has anybody ever heard of that? No? Back of the room? Yoo-hoo. Have you ever heard of it? No? Surprised? Okay. It comes up in communication theory quite a bit. Anyway, it's not an unknown type of equation, and a lot of people have thought about it. Okay. So let's see what we have. We have an arbitrary inter-arrival time distribution, an arbitrary service time distribution, one server, as I said. Again, I want to repeat, first come, first serve. And let's recall the notation. Cn is the nth customer to arrive. That customer arrives at time tau n. The time between his arrival and the previous guy is called tau n, is equal to, I'm sorry, little tn. Little t n is tau n minus tau n plus 1. Xn is the service time of the nth customer. And W sub n, the thing we want, is the waiting time in Q for Cn. Everything besides Wn is given to us. We know when they arrive statistically, and we know how long they spend in service. So the question is there an embedded Markov chain or a Markov chain we can exploit? Well, there's memory in the interrivals, and there's memory in the service. So it looks like we're in trouble, okay? But one thing we might consider is something I showed you one time before, something called U of t. U of t, if you may recall, is the unfinished work. That's what the U stands for. Unfinished work in system at time t. And what does unfinished work mean? It means if that instant nobody else arrived, how long would it take to empty the system? How much work do you owe the customers who were there? And we've drawn pictures of it. I'm going to draw another picture of it shortly, okay? And by the way, this unfinished work is sometimes called the virtual waiting time, V, because it is the waiting time of a virtual customer who could arrive at time t. How long will he have to wait when he comes? It's all the work that's there when he arrives. What he adds is not his waiting time. That's the time he spends in service. So some people call this V of t for the virtual work, but I prefer unfinished work because it's much more expressive. Okay. Well, U of t is not a Markov process because at any point in time, if I tell you how much unfinished work there is, at any point in time, is anything else you need to know how that thing proceeds? Remember, the unfinished work, let's draw a typical picture. If I draw U of t, at some point it's got some value, and if nothing happens except time evolves, what happens to the unfinished work? It goes down at what rate? At what rate can you discharge work? 1 second per second. So go down at slope -1, right? But what can happen? What can happen? Excuse me? A new arrival, right. So let's put in such a new arrival, say here. At that point, what happens to the unfinished work? It jumps up by how much? How much work that customer brings in, and how much work does he bring in? He brings in his service time. I want 3 seconds of service. So it'll go up, let's say it's 2 seconds of service. It jumps up like that. And then it continues on down, et cetera, et cetera. That should be a very straight line. Let me redo that. Let's assume there's another arrival here, and then bang, empties. Those are straight lines, I'm sorry. So is U of t at an arbitrary point in time a Markov process? I've already told you no. The question is why not? What about the past can affect how that curve behaves in the future? If I give you the value of the unfinished work, say, at this point in time, t, say t0. I'll give you the value right there. Is there anything about the past that can help you predict what the rest of the black curve looks? I want to clean up the black curve. It's really ugly.
Yes.
What is it?
How long it can be since the last customer to service?
Not quite. Not quite. You're close, but not quite. Oops, I can't draw straight here. What can affect the way this black curve behaves in the future besides knowing its value right here, right there? Yes? Right. How long has it been since the last arrival? Because the next arrival, when this thing occurs here, depends upon, it's got memory. It's not exponential. So that could affect statistically when it's going to jump next. So there is memory. Shucks. Except, when is it memoryless? At the arrival times. At the arrival times, these values right here, let me use another color here. Let me use green. These values right here do form a Markov process, because there's nothing about the past that can help me predict the future any better than the value at those green dots. I know it's been 0 seconds to last arrival, and why don't I have to know the service time? Because the unfinished work already contains how much unfinished work, how much service I owe the system. So you can see there's the essence of a better Markov chain here. And that's what we're going to exploit, okay? So we're going to use those points, and we're going to use that piece of the expression. So that's a Markov process. I want to study that Markov process. Markov process at the arrival instance. For u of t. Okay, so let's examine that. So let's see how I can express some aspect of this. So let's redraw this picture now, because I have to put a lot more detail into it. Let's assume that Cn arrives right here at some point. I'm sorry, I don't want to draw. I want to draw the Qn server. I'm sorry. We'll draw the unfinished work shortly. Once again, as always, this is the server. This is the queue. We get an arrival, say, right here. That happens to be Cn. And suppose he has to wait. So at some point later, he goes into service. And at some point after that, he departs service. So that's the history of Cn. Now let's watch the next guy come in. Let's watch the n plus first come in. He's going to come in somewhere. I don't care where. I'm going to put him arbitrarily here. And when does that customer go into service? It's first come, first serve. When will Cn plus 1 go into service? Excuse me? Exactly, when Cn leaves. So Cn plus 1 enters service right there. And he hangs around for a while. Okay, now let's label some things. I want to put some indicators here when Cn arrives. Let me use these nice lines. I need to put an indicator here when he goes into service. And I want to put an indicator here when Cn plus 1 goes into service. And I'm going to label some things. First of all, I'm drawing a period here. Can someone tell me, do we have a symbol for that period? What is that interval? Yes? Idle time? No, it's just as Cn is there. Cn couldn't even go into service. Somebody else is in service. Time in Q. We have a symbol for how long that is. Wn, exactly. That's the waiting time in Q, right? And now I'm doing another interval here. Oops, let me make this as pretty as I can. What is that interval I just drew? Xn, the service time for the nth customer, right? But there's more. What is this interval I'm drawing down in the lower left? Inter-arrival time, it's Tn plus 1. And by the way, as I write that down, I believe I used the wrong, this should have been a plus 1 here, yes? Time between n plus 1 and n. That's what I'm drawing here. Because the arrival time for Cn is tau n, arrival time for Cn plus 1 is tau n plus 1. And while I'm at it, there's another interval I ought to identify. This interval right here, what is the one I just drew? Wn plus 1. That's how long Cn arrived here, and he goes into service here, so the time he spent there is W sub n plus 1. And this is what I'm going to call case 1. And case 1 is the case where Cn plus 1 arrives before Cn leaves. So what can I say? There's obviously, there's two intervals here. This interval here is the same as this interval here, so I'm going to equate that. So let's just say that Tn plus 1, the thing on the bottom, plus W sub n plus 1 is equal to Wn plus xn. And that's assuming that this quantity is 0, is greater than 0. So let's say that if Wn plus xn minus Tn is greater than or equal to 0. Namely, the next customer didn't arrive too late. Now, there's a case 2, and this is the simpler case. Let's draw axes again. And here we're going to get Cn arriving someplace, say here. At some point, he's going to go into service, and he's going to leave. And only after that does Cn plus 1 arrive. So let me label some of these things. This is Cn, Cn, Cn. This is Cn plus 1. Now let's draw some intervals again. I want a line here when the customer arrives. I want to know when he goes into service. I want to know the time between the two arrivals. So what is this axis once again? What is this thing I'm trying to label now? What is that interval I just drew? It's the waiting time in Q for Cn. And this little interval here is a service time. And this interval here is Tn plus 1, the time between arrivals. So in this case, what are we going to get? We're going to get basically that Wn plus 1, the thing I'm after, how big is it? 0. Exactly. And that's if Wn plus xn minus Tn plus 1 is less than or equal to 0. So, in fact, let me, up here in case 1, just solve this tiny baby equation, which says that W sub n plus 1 equals Wn plus xn minus Tn plus 1. So I have two expressions for Wn, case 1 and case 2. Okay. So I want to define an obvious and important random variable, difference between service time and inter-arrival time. Define this variable U sub n is equal to xn minus Tn plus 1. That's a definition. And by the way, I'll warn you now, we will need the expected value of U sub n to be less than 0 for a stable system. That means the amount of work you're bringing in, xn, is less than the amount of time you give the system to do that work. Because every little tn, you're bringing in an amount xn. You better give enough time for that xn to be discharged. If it was coming in faster, you're going to get a Q. So we need this, basically, okay? So let me now combine these two cases. Okay? And that means that W sub n plus 1 equal to one of two things. Either it's Wn plus this new variable U sub n, if that's greater than or equal to 0, if Wn plus Un greater than or equal to 0, or it's 0 if Wn plus Un is less than or equal to 0. And I'm going to give this equation a number. I'm going to call it a single star in red. Oops. Those star equations, just temporary notation. Okay. Now let's make a comment. The comment is that W sub n plus Un is the following. It's equal to the sum of the unfinished work found by Cn. He comes in and he finds that much. Why? That's what the Wn is. Plus his service time, which is xn, which adds to the unfinished work, less the time per n Tn plus 1 until the next arrival, whose next arrival? Cn plus 1, which subtracts from the unfinished work. This is just restating the obvious. So in other words, it's Wn plus xn minus Tn. When you come in, I'll go back to this picture here, you come in and you find an amount W sub n right here. You add to it the service time xn, and you subtract the amount of time until the next arrival, which occurred over here. This was the next arrival, obviously. And that's how much he finds. So he finds what the previous guy found plus what he brought, less the time you were allowed to do work. That's exactly what this whole equation says. This makes very good physical sense. We're using our engineering smarts here, if you will. Okay? Okay. So I want to rewrite this equation on top. Rewrite equation star simply as W sub n plus 1 equals the maximum of 0 and Wn plus Un. So I've simplified, I've now got a single equation with a somewhat complex operator. More than that, I want to simplify that, so I'm going to make a definition, which you've seen before, or hopefully you have, if not, here it is. I'm going to say a quantity, say x, with a plus sign around a parenthesis, is defined to be the maximum of 0 and x. Which means that Wn plus 1 is equal to the quantity Wn plus u sub n plus. Again, somewhat shorthand notation for this very important equation. Basically says if you have a quantity x, you're only looking at it on the non-negative half line. And everything on the negative half line is put at 0. And we may or may not get to this, but there's something called a sweeping operator. This is on the side, so you don't have to know this for the exam, okay? Suppose I had a function, a probability function that looked like this. Say that's f of t. F of t plus would look like this. It looks like the same thing over here, if I can draw that funny thing again. Plus an impulse right here, which is the area of all this. It doesn't actually use the plus operator. That's called a sweeping operator. You're sweeping all the probability in the left-hand line into the origin. And it's related to this plus operator. Just give you a little clue how this is used very effectively. That I'm going to mark this in, don't worry about this, but that's called a sweeping operator. If you ever come across it in your casual reading. Okay. So let's look at this equation we have now. It's a very important equation. In fact, I'm going to mark it in red. It's so important. And I'm going to give it a notation 2 stars. I'll refer to it on and on. Okay. Now, how does Wn plus 1 depend upon the previous variables? Okay. So let's say that Wn plus 1 depends upon the whole sequence of waiting times in the past, namely W sub I for I equals 0, 1, up to n. So Wn plus 1 depends upon all the previous W's only through Wn. Sounds like a Markov process, right? Plus a random variable un which is independent of all the other wi's. Of all previous wi's. After all, the inter-arrival time and the service time doesn't depend upon at all waiting times in the past. You choose it independently from A of t and B of x. So looks at Wn plus 1 only depends upon the previous Wn, the most recent one. That's a Markov process. That's what we mean. Okay? Okay. So let me just say that. Thus, the sequence W0, W1, W2, ... is a Markov process. Now let's solve this red equation recursively, okay? So let's start with W1. W1 equals W0 plus U0 plus. Fine. Let's write W2. It's equal to W1 plus UN plus, which is equal to the max let's expose the max operator now, of 0 and W1 plus UN. That's the definition, which equals the max of 0. And what's W1? W1 is the max of W0 and U0, or U1. So let's write down U1. That's a possible max. Or the max of 0 and W0 plus U0. Which can be written, I'm going to slide over a little bit. Oops. That's equal to the max. Let's break that max inside the bracket now. That'll be the max of 0, comma, U1, comma, U1 plus U0, comma, and then plus W0, I'm sorry, plus W0. Let's go one more. Let's do W3. That's the max. That's basically W2 plus U2 plus, which equals to the max of 0 and W2 plus U2. And we know W2 from the line above. So that's equal to this big baby. It's equal to the max of 0. That's one possibility. U2, I found out from the line above. That's a 2 here. And then the max, this last term, is the max of 0, comma, U1, comma, U1 plus U0 plus W0. Which is simply equal to the max of 0, comma, U2, comma, U2 plus U1, comma, U2 plus U1 plus U0 plus W0. So in general, we'll get that W n itself, after you go through this, is equal to the max of 0, comma, UN minus 1, UN minus 1 plus UN minus 2, comma, dot, 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 out through, and let's get to the last two terms, UN minus 1 plus UN minus 2 plus dot, 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 plus U1. And then the last term is a similar thing. It's UN minus 1 plus UN minus 2 plus dot, 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 plus U1 plus U0 plus W0. Okay. But the sequence of U sub i's is a sequence of identically distributed independent variables. IID is a sequence of IID, identically distributed independent random variables. So we can interchange them. They're interchangeable. They all have the same distribution. So now consider a new random variable, Wn prime. That's a new random variable with the same distribution as Wn. And what is Wn prime? It's defined to be just like the equation at the top of the bottom of the page above, which is the max of 0. And instead of u n minus 1, I'm going to start off with u0. After u0 and un minus 1 have the same distribution. And then add one more to it, u0 plus u1, comma, dot, 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 all the way out to u0 plus u1 plus dot, 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 plus u sub n minus 2, comma, and then the very last term is u0 plus u1 plus u2 plus dot, 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 all the way down to un minus 1. And finally, we add to that w0, the initial waiting time. Simple change of variables. And they're all identically distributed. Now, this is getting a little cumbersome, so let's make a new definition. Let capital U sub n be defined as a sum of these u's. Namely, it's a sum from I equals 0 to n minus 1 of little u sub I. And define u sub 0 to be 0. That means that Wn prime is equal to the following. It's equal to the max of, we started with 0, but that's u0, comma, u1, comma, all the way out to un minus 1. Then finally, un plus little w0. So just trying to keep track of these little u's. Now, we'll assume there's an initial condition that says the waiting time for the initial customer 0 is 0. First guy comes into an empty system, just to get this thing started. And we're going to get rid of the transient as we let n go to infinity. OK. Then, Wn prime can only increase with n. If you look at Wn prime, it's a max of one thing or another thing or another thing. As you add more things, you can't make the max smaller. If the new thing is less than something else, it doesn't count. If it's bigger, it adds. So it can only increase with n. And by the way, that's an n, not a u. I don't write it carefully. Let me be very careful there. With n. OK. All this is to come up with the following conclusion. Therefore, the limit of w sub n prime as n goes to infinity must converge to the, and it parens, possibly infinite random variable, which we've always called w tilde, the waiting time random variable. Now, this embedded Markov chain is ergodic. It, as I said before, if with probability 1, the waiting time is finite in the limit. And if so, Wn prime and Wn both converge to W. The thing we're after, the waiting time random variable. And then what we're after, and then the distribution of W is the waiting time distribution itself that we're after. And as I indicated before, I'm going to tell you again, our friend Lindley, before we get to his equation, Lindley is shown, as I indicated before, that if 0 is less than the expected value of the absolute value of u sub n, this key variable, and if that is less than infinity in particular, then the system is stable, namely it's ergodic. If and only if that expected value of u itself, u sub n, is less than 0. Namely, rho is less than 1. That's the same thing, okay? So let's assume that's true, that we do not have an overloaded system. Let's assume the expected value of u sub n is less than 0. Average service time is less than the average inter-arrival time. And of course, if you want to write out what that is, the expected value of u sub n is the expected value of xn minus tn plus 1, its definition, which is the expected value of xn minus the expected value of tn plus 1. Expected value of xn is just x bar. Expected value of tn plus 1 is just t bar. And that's equal to t bar times rho minus 1. Therefore, we need rho less than 1 for the expected value of un to be less than 0. So that's consistent. Okay. So that's just getting warmed up. So now let's go after this thing. Now let's recall what we're after. Recall that the limit, as n goes to infinity, of the probability that the waiting time is less than or equal to y is equal to the limit, as n goes to infinity, of the probability wn prime less than or equal to y. Namely, you have the same distribution. And that limit, in both cases, is what we have been calling capital W of y, the baby we're after, the waiting time distribution for GG1. And it will exist for rho less than 1. So let's now set up, let's find W of y, which is the whole reason we started this discussion in the first place. But now we have a couple of tools, okay? So, but I have this new random variable u. Let's define its distribution. Let's define. And you have to be careful of my penmanship here, okay? Capital C, that's a capital C of u with a sub n on the C as, in definition, the probability that u sub n, which, by the way, equals xn minus tn plus 1, that's less than or equal to u, some quantity u. So capital C is the distribution for the random variable u sub n. That's u sub n right here. And notice that u is not restricted to the positive half line, as most of our other random variables. xn was distributed to positive half, non-negative half line, and so for the interarrival time. They had to be non-negative. U can go negative, and particularly we wanted to go negative to go stable. Okay, so let's keep that in mind, okay? So let's go after this guy. So C sub n of U. It's equal to the thing above. Let's condition it now. Let's leave room for an integral sign. I want the probability that it has a certain value which is xn minus tn plus 1 is less than or equal to u. But now we're going to condition it on tn plus 1 equals some number t. And if I want the unconditional, I have to integrate over all possible t. So integrate this from t equals 0 to infinity dA of t, where a is the interarrival. I said, what if the interarrival time was t? Then what's that probability? Then unconditional multiplied by the probability interarrival time is t over all possible values of that interarrival time. Now, if you look at xn minus tn plus 1, xn is independent of tn plus 1. The service times don't care about the interarrival times. So I can write the thing above, that capital C sub n of u, is equal to the integral t equals 0 to infinity of the probability that xn is less than or equal to u plus t, and then, so given tn plus 1 equals t, that's a plus 1 above. The equation above needed tn plus 1, not tn, is equal to t dA of t. But again, service time is independent of tn plus 1. So we get that cn plus u, cn of u, is equal to the integral from 0 to infinity on the interarrival time. And what is, let me just write it. What is this thing? First of all, x doesn't depend upon the condition. So you can forget the condition, and what is the thing that's now circled? That's the service time distribution. So that thing is just capital B of the argument u plus t. All of that dA of t. And notice it's independent of n as expected. So I can write C sub n of u is equal to capital C of u with no index. Okay. Now I haven't defined the random variable u yet. Let's do it right now. We're going to let u tilde be defined, of course, as x tilde minus t tilde. Doesn't depend upon the index. And I'm going to give a name to this equation we have on the right here. I'm going to give it 3 stars. Now, that equation, the 3-star equation, that looks like a convolution, doesn't it? If you wrote dA of t as little a of t dt, but what's missing? It's not quite a convolution. What's wrong with it? You probably forget what a convolution equation looks like. There's a minus sign missing in the argument of b. Okay. Okay. So we need the difference rather than the sum. So using, oops, using this notation for convolution, as always, nothing to do with the red stars, of course, we therefore got the density C of u, which, by the way, is the same density for u sub n, because it doesn't depend upon n. It can be written as the convolution of a and b, but not quite. It's a of minus u, b, convolve with b of u. And I just put the minus sign in the a condition, under the t. In other words, I put the minus sign right in there. It's got the wrong sign, so therefore it's a of a negative argument. Okay. That's an important equation. That tells us how this very interesting random variable u, whoops, is related to a and b. Yeah, I guess we'll stop now. On Wednesday, we're going to finish this. We're going to take this all the way to a very nice algorithm for finding the GG1 solution. Okay? And we may have a few minutes left over, so I can bother you with some other ideas as well. Okay? So I will see you on Wednesday. Oh, it's in my pocket. Here. Do your job. Thank you. Okay, so